Dear students, welcome to Digital System Design using Verilog class. In today's class, I am going to explain you about sequential basics and some concepts related to state transition diagram. So coming to the sequential basics, sequential circuits will make use of current inputs as well as previous inputs in order to produce the output. So there will be a storage element, there will be a gates. So altogether the combination of all this is a sequential circuits. So usually the sequential circuits are governed by clock signals. It is controlled by the clock signals. Best example is flip-flops. In that D-flip-flop is considered here. In the textbook, the author has considered D-flip-flop as a basic component for the explanation of all the sequential circuits. So D-flip-flop, it is a 1-bit storage element which is considered as a basic component over here. So it is having D input, there will be a clock to control the input, Q is the output. As you can see that there is a clock signal. As soon as we provide the input and when the clock is high, is at the positive edge of the clock signal, you will get Q, that is output is equal to the input. Okay, so when the input goes low, in the immediate next clock pulse the output also has gone low, that you can notice at this instance. So there are many other kinds of flip-flops available like set and reset flip-flop, which is called as SR flip-flop, JK flip-flop, T flip-flop, which is also called as toggle flip-flop. So that is about sequential circuits. And there are something called as finite state machines, FSMs. Before to that, let us have a look into this data path as well as control path. In digital system, so many computations has to be done. So sequence of operations will be done on the data by using data path as well as control path. So what is this data path is nothing but combinational circuits are used for the execution of so many operations on the data. So similarly, registers for storing intermediate results will be done. So this is called as data path. By taking the signals from the data path, there will be a separate section called as control section, which is going to do controlling sequence. So basically this control section generates the control signals for the selection of operation. What operation has to be done on the data will be done by selecting a suitable operation from the control section, and it also enables the registers at the right time to store the values in order to pass the values. So basically this control section makes use of status signals from the data path. Let us consider an example to understand data path as well as control section or control path using this complex multiplier. So complex multiplier is having multiple operations to perform. It makes use of 4 multipliers, multiplies, 1 addition and 1 subtraction. So sequentially it is done using 1 multiplier, 1 adder or 1 subtractor at a time. So you can have a look at this. This is a data path where a multiplier is used at the first section. These are the set of inputs. First input, this is the second input. Multiplication is done here. It is passed through the flip-flops. Either an addition or subtraction will be done and the resultant will be provided at the output. So this is a data path which is written in Verilog also. Control sequence is generated by taking the data path into consideration. You can see that this is a first operation. A underscore R is multiplied with B underscore R. AI is multiplied with BI. So the first the difference of these two is obtained here. Next is AR with BI, AI with BR. So PP1 and PP2 has been obtained. So addition has been done. So multiplication, subtraction, multiplication and again addition has been done. So totally 6 cycles has been taken. So this is a control sequence. what operation has to be done is controlled by the control section. Apart from this, there are something called as finite state machines, which will make use of state transitions in order to define the digital system. So state transition diagrams, you can see that in the diagram S1, S2, S3 are the different states which is represented in the bubble. The edges, what you are seeing is the transition from one state to the another state. These are the conditions, right? When the state of the operation is S1, the transition from S1 to S2 takes place when the inputs are 1 and 0 or 0 and 1. When the inputs are 0 and 0, it remains in the same state, that is S1. Similarly, when the transition has to take place from S2 to S3, input should be, there are no inputs in order to say, in order to have a transition from S2 to S3, because whenever the operation comes to the S2, by default it is going to get transition to S3. Similarly, in S3, if the transition has to take place from S3 to S1, input should be either 0 0, yes, it has to be 0 0, so that it come back to S1. Otherwise, if the inputs are 0 1, it remains in S3. If the inputs are 1 0, it remains in S3. If the inputs are 1 and 1, it remains in S3. So different states are considered for different status of the system. So transition happens depending on the suitable inputs that has been considered. So apart from this, by making use of the flip-flops, it is possible for us to go with timing. So we have to consider timing of the circuits, right? So this gives you a brief overview of what exactly a clocked synchronous timing is all about. So have a look at this. Clock, total time is TC, and Q is output of a D flip-flop, D is input. So propagation delay, slack time, setup time, everything is provided over here. So you can notice that the state transition from clock to the output, there will be a certain amount of time that is taken. In fact, practically there will be a certain amount of time is taken to generate the output as soon as there is a transition in the clock. When inputs are high, clock is also high, output changes to high with certain amount of delay. So that is what clocked synchronous timing is. So control path timing, by considering all the time involved in the circuit, and there are something called as synchronizers. So synchronizers is nothing but just hold the value for certain amount of time. So that is what sync in. Asynchronous input has been given as an input, and synchronized value will be taken as a output. So input changes. If the input changes outside the hold time or setup time, it has to be bring back into the common synchronized timings by providing a delay. So that delay is generated by using one additional flip-flop or one clock cycle of time. So that has been generated by using 2 D flip-flops. One clock pulse will make this input to pass through this D flip-flop. Next clock pulse will make that input to pass through it. So totally 2 clock cycles are involved in this particular circuits. So intentionally we have delaying in order to generate the synchronous operation in the circuit. So those are called as synchronizers, right? So this is about the first module. We will be discussing about all these topics in detail in the class.